Okay, you can start now. Good luck.
Thank you. So good evening, we are the Boeing Constrictors, and this is our presentation on the design development of our BC-1 Rock Python austere airfield light attack aircraft. I'm Alexander Black.
I'm Henry Dorking.
I'm Alexander Gaskins.
I'm Bradley Lawes.
I'm Vivek Tolani.
I'm Kyle Worley.
And I'm Yoni Zigden. And next, we're going to be talking about the objectives and requirements for this aircraft. So to begin, we wanted to establish a clear objective, and this was to create a light attack, close air support aircraft. And throughout the presentation, we will discuss how these requirements listed on the bottom left will be applicable to our design. And on the top right, you could see the design mission. This mission was specifically meant to kind of simulate a low to the ground, low altitude attack to ground forces that would only be possible by helicopter previously. And then on the bottom right, you could see the ferry mission. The ferry mission will be our Rock Python's way of transporting from one location to another with or without payload. Next slide.
After an initial weight estimation of the BC-1, the design process was able to begin. The first component to be designed on the aircraft is the wing, and to start with the wing, the group had to select an airfoil. The Boeing instructors decided to look at various NACA airfoils that were located on various light attack aircraft operated by the U.S. Air Force in the late 20th century. These NACA airfoils were then taken into the X-foil software, and various coefficient of lift and coefficient of drag versus alpha plots were generated and used to compare the airfoil's performance directly against one another. After completion of a design matrix, the NACA 2417 airfoil was chosen as the BC-1 Rock Python's main wing airfoil, as it featured well-rounded performance while also having the lowest drag coefficient at zero angle of attack and the highest stall angle of attack, leaving plenty of room for the aircraft to operate and rotate, increasing the short takeoff and landing capabilities of the aircraft. With the airfoil selected, the rest of the wing is able to be flushed out. A trapezoidal wing design is selected, and a wingspan of just under 46 feet is chosen, as is the average of the various light attack aircraft studied in the airfoil selection process. A high aspect ratio of 5.7 increases the coefficient of lift and the general performance of the wing. Using this aspect ratio in the wingspan, we're able to calculate a reference area of just under 363 feet squared. The wing is placed at an incident angle of 1 degree on the aircraft, as the NACA 2417 airfoil had the lowest coefficient of drag at this 1 degree. A sweep of 2 degrees is chosen to balance out the increased cost and manufacturing complexity of a sweep angle, while also reaping some of the benefits that a sweep angle provides, such as decreased detection. Using this sweep angle of 2 degrees and studying various other aircraft with similar sweep angles, we were able to select a taper ratio of 0.45. This allows us to find the root chord to be 11 feet and the wingtip chord to be just under 5 feet. A twist of 3 degrees is placed at the wingtips, allowing the wing to stall at a higher angle of attack and also increasing the short takeoff and landing performances of the aircraft. Finally, leading edge slats and trailing edge Kruger flaps are placed in the wing to increase the lift during low speed operation, once again, meaning the aircraft can take off and land at lower speeds, increasing the short takeoff and landing performance. With the wing fully designed, we were able to take it into the SolidWorks flow simulation and analyze various flight conditions. These flight conditions are takeoff, cruise, and landing. For each of these scenarios, we were able to generate a coefficient of lift of the wing. For takeoff, this value was 1.21, cruise it was 0.33, and landing was 1.24. Significantly, the landing velocity was able to be 195 feet per second, so it's pretty low value. We wanted this value to be lower, as it allows the aircraft to touch down with a low speed, thus decreasing the distance we were required to stop.
After the wing was designed, the next step was to select the power plant. We quickly chose a twin engine design, as this is a military aircraft, so we wanted to have engine out survivability. So in an engine out, scenario, a twin engine aircraft is much more likely to survive, be able to make a controlled landing, or even potentially complete the mission if it's still flying on one engine. There's added benefits to having twin engines over a single engine. One is that a twin engine aircraft has increased crosswind resistance, so we can land and take off in less favorable conditions as dictated by the austere field requirement. Another one is with the wing-mounted twin engine layout, the center of gravity envelope is much narrower since we don't have the heavy engine in the nose of the aircraft. This let us push the wing further back on the body, as you can see in the graphic there to the right. And this increases the maneuverability of the aircraft. Next slide, please. The actual engine that we chose was the PW123 by Pratt & Whitney. This is part of the PW100 series, which has been in service since 1984. It's flown around the world on military and civilian aircraft. It's very reliable, very low risk object. The PW123 puts out 2,400 shaft horsepower. So between the two that we have on our BC1, we'll have 4,800 shaft horsepower. It's got a very competitive specific fuel consumption and a reasonable weight. And as you can see on the slide there, it more than matches the required horsepower that we calculated our design requires. Next slide, please. Next was the propeller design. So we went with a custom 3-bladed design. As you increase the number of propeller blades, you lose propeller efficiency. We wanted to keep that very high. So we use this NACA 6409 airfoil with a 40-degree twist angle, as you can see in the graphic on the right. That 40-degree correlates to a high propeller efficiency for a 3-bladed design. And for our almost 7-foot diameter propeller, we calculated a propeller efficiency of 85%. We then calculated the required propeller efficiencies for various performance regimes, including takeoff and cruise, and found that our design successfully completed those requirements. Next slide, please.
So before talking about the design of the fuel tanks, I wanted to take the time to talk about the fuel's properties that were important in determining how much fuel the aircraft should carry. So as you see in this slide, the fuel density ranges from a lower value to a higher value. And in our calculations, we considered the lower density because we wanted to calculate the maximum amount of fuel that the aircraft should carry to be on the safe side. And this makes sense because with the lower density of fuel, that means that more fuel would be needed to operate the aircraft. And for a similar reason, we considered the weight difference in the aircraft in the design mission rather than the ferry mission, because the design mission requires the aircraft to cover more range. And the weight difference of the aircraft is equivalent to the weight of the fuel that the aircraft should carry. And within the fuel, we included a special foam, which makes the fuel fireproof and explosive proof. So instead of carrying just a fuel amount of 646 gallons, the aircraft, BC-1 aircraft, is required to carry 685 gallons of fuel and foam, since foam displaces 5% of the fuel volume that it's put into. Next slide. So we decided to integrate wingtip tanks into our BC-1 aircraft, because we wanted to take the advantage of the fuel weight. And what I mean is when the wingtip tanks are on the tip of the wings along with the weight of the fuel, this would reduce the tendency of the wings to flutter around. And the reason why we would want to reduce the tendency of the wings to flutter around is because when it flutters, it causes fatigue in the wings due to it being subject to a lot of bending moment loads. And also the wingtip tanks provides a little bit of aerodynamic benefits, such as reducing the vortices that are usually created on the tips of the wings as a result of lift-induced drag. Next slide, please. So I want to take a moment to talk about self-sealing bags because we have a self-sealing bag within the wingtip tanks, and the fuselage tank itself is a self-sealing bag. So as you can see on the bottom of this slide, the self-sealing bag consists of 3 different layers. And how it works is that when a bullet penetrates the bag and creates a hole, initially fuel will start to leak through the hole. And after that, the untreated natural rubber will combine and absorb the fuel that starts leaking. And this will cause the untreated natural rubber to expand and cover the hole that was created by the bullet. Next slide. So we decided to keep the fuselage tank in the same location as the wing so that we could shift the center of gravity of the aircraft as close to the aerodynamic center of the wing as much as possible. We also decided to put the fuselage tank underneath the wing so that we could shift the CG as low to the ground level as possible. Overall, that would increase the stability of the whole aircraft. Next slide.
Yeah, so now it's time to design our fuselage. When designing our fuselage, we first considered a fitness ratio between 6 and 8 for common aircrafts. And so we chose 6 for our light attack configuration. And from this fitness ratio and experimental data and the known takeoff weight of 27,000 pounds for our aircraft, we're able to come up with a length and diameter for the aircraft based on experimental data. And this design fuselage, then from the design, we were able to get a volume of 1,616 cubic feet. And this was plenty sufficient for carrying our loadouts, fuel tanks, and crew station. Next, it was time to design what kind of structure we would be using in our fuselage. And a semi-monocoque was clearly the best option for us. It offers extremely high damage tolerance and ease of maintenance and repair. Just being able to replace any fuselage panels that were damaged by cracking or corrosion in battle could be extremely beneficial and lower our prices of maintenance and repair. And next, the materials were decided. Aluminum was chosen for the skin, stringers, and bulkheads because it offers low weight and good sufficient strength for the application. And the next, steel was chosen for the longerons to just confirm that the maximum bending stresses found in the fuselage would be attained for. Next slide.
So for designing the BC-1 Rock Python's landing gear, we looked towards modern day aircrafts, and from that, we were able to select the tricycle landing gear arrangement, which allows for a high degree of stability while also providing increased forward visibility. And with our landing gear arrangement selected and taking our airfoil into consideration, we were able to determine a maximum tip back angle of 20 degrees. And from this, we ran through an iterative procedure to determine wheel locations for the BC-1, resulting in the nose gear being 6 feet forward of the center of gravity, the main gear being 1 foot after the center of gravity, and the main gears being 8 feet away from the center line. We combined these locations with our estimated aircraft weight to determine the static load that each wheel would experience. And then following this, we were able to use empirical formulas to roughly size the tire diameter and width. And this allowed us to get a contact area. As another form of static analysis, or as another form of wheel analysis, we performed a kinetic energy analysis to determine wheel size. And this ended up resulting in a sizing that was much smaller than our static load analysis. So for actual wheel sizing, we went ahead with the static load analysis. We consulted the Goodyear Aviation tire data, and that allowed us to select a wheel size of 8.5 to 10 for the nose wheel and 15 to 16 for the main gears, resulting in a diameter of 26.3 inches and a width of 9.05, as well as a diameter of 42.4 inches and a width of 15.3 respectively. Next slide, please. And for shock absorbers, we considered various designs from solid bars functioning as springs to oleos. In the end, we decided to go with the levered oleo shock strut because it can handle shock absorption better than other designs, and the lever geometry allows for less deflection while also modularizing the design, which allows for faster repair times since the entire landing gear doesn't need to be taken apart. This design also allows for a smoother ride because the wheels can deflect aft on rough terrain, allowing for the wheel to have more travel time over an obstacle. With our previously estimated landing velocities and a tire stroke, we were able to calculate an oleo stroke size that we needed, and thus we could size our entire landing gear. The Boeing constructors ended up deciding on a metered orifice oleo because it operates at a higher efficiency than a fixed orifice. And additionally, we decided to design retractable landing gears to reduce aircraft drag in flight, with our nose landing gear retracting aft into the fuselage and our main landing gear retracting into the engine fairing. Next slide.
For the tail design of the BC-1 Rock Python, we went with a conventional design, single vertical tail and a typical horizontal tail. This is just to save manufacturing costs. This is simple and cheap, time proven, and will bring down the manufacturing cost of complexity. For the dual engine configuration, we have a very large vertical tail comparatively with a 60 square foot area. And the horizontal tail is kept in line vertically with the main wing of the aircraft. And this prevents the main wing from blanketing the horizontal tail in nose up configurations or stall scenarios, meaning the pilot will be able to maintain control and recover from any bad attitudes that they get into. And for our tail, we're using a NACA 0007 symmetric airfoil. Next slide, please.
Following the tail design, the next step in the design process was the ordnance selection for the BC-1 Rock Python. The constraints of our design, such as a 4,000-foot austere runway and a 3,000-pound payload, not including the mounted gun, kept the weapon selection limited. The weapons must be balanced across the longitudinal axis, and as such, most weapons are added in groups of 2. With a cruise speed of 400 feet per second, wave drag as you approach the speed of sound is not encountered on the airframe, and as such, not on the weapon selection either. This allows weapon placement via pylon as the optimal choice, as an internal bomb bay would add extra weight for little drag reduction. 3 separate layouts were selected in order to give a variety of attack options with a variety of weights. Next slide. The first loadout selected was the heavy bomb package. It is composed of 5 Mark 82 large diameter general purpose 500-pound bombs. 3 bombs are mounted under the fuselage while the remaining 2 are mounted on the wings. The wing mounted bombs were placed as close to the fuselage as possible in order to reduce the loading experienced by the wing root along with roll stability considerations. The design of this ordnance grouping package is to hit fortified static positions. The bomb release mechanisms are industry standard for all pylon ordnances. This package is the lightest of the 3 with a total weight of 2,500 pounds. Next slide, please. The second loadout on the Rock Python is a mixed bomb package. It is composed of a single Mark 82 large diameter general purpose bomb and 2 GRU bomb carriages. Each carriage contains 4 GRU small diameter 285-pound bombs. The single 500-pound bomb is mounted under the cinder line of the fuselage while the remaining 2 carriages are mounted on the wings. The purpose of this package is to hit a variety of targets, both mobile and static. A greater number of individual options can be selected through this mixed bomb package, although it is over 600 pounds heavier than the previous package and has a total weight of 3,160 pounds. Next slide, please. The final ordnance setup is the rocket package. It contains a single Mark 261 rocket drum containing 19 2.75-inch Hydra unguided rockets mounted under the fuselage. There are also 4 AGM-65 air-to-ground missiles mounted under the wings. The M261 utilizes the standard hardpoint, while the AGM-65 utilized the LAU-117 mounts. The purpose of this package is to target smaller, more mobile objects from range. The rocket package is the heaviest package of the three and has a total weight of 3,240 pounds. Next slide, please. The M2 Browning 50 caliber machine gun was chosen to be the mounted gun for our design. 2 guns will be mounted in the nose, each with 500 rounds of ammunition. The primary purpose of the gun is for soft ground targets. The secondary purpose of the weapon is for self-defense and targeting other aircraft in the area. Along with the M2, most of the weapons were selected to be low cost and smaller in size than traditional ground attack aircraft due to the overall size and operation field conditions that are expected of the BC-1. Next slide, please.
One of our major considerations when designing the BC-1 Rock Python was the survivability of the aircraft. This can clearly be seen in previous sections through the self-healing fuel tank and through the design that allows the aircraft to fly on a single engine. One of the other survivability considerations we took into play were stealth considerations. The number one stealth consideration we decided to tackle was radar detectability. Radar detectability is the number one way of tracking aircraft nowadays, and two of the general ways we were able to tackle radar detectability were one by angling and sweeping surfaces along the aircraft, which can be seen in the wings below, and number two was hiding the weapons within the body of the aircraft to reduce surface area for the radars to bounce off of. Both of these allow the radar waves to hit the aircraft, and it directs them in different directions rather than sending them back to the radar that initially sent the waves. The second form of radar detectability we decided to tackle was the infrared detectability. And the first way we did this was by using a prop aircraft over a jet aircraft, because a prop aircraft has a high bypass ratio when compared to a jet aircraft. And this high bypass ratio allows the engine to stay cooler, making it less detectable on infrared radars. And we also decided to use anti-sun glint paint. As seen in the first picture of the aircraft below, this is anti-sun glint paint. It's not as shiny. It doesn't allow sun to bounce off the aircraft as easily and be detected by infrared radars versus the aircraft under it, which is extremely polished and allows sun to bounce off easily and be detected by radars. Next slide. The other stealth considerations we took into play were visual detectability, and once again, the high bypass ratio for the turboprop comes into play because this allows the engine to stay cooler in comparison to a jet engine, because jet engines actually have the capability to heat up enough to the point where they will potentially glow red at night, and having a high bypass engine reduces the chances of our engine glowing red and being visually detectable at night. The anti-sun glint paint also comes into play because it makes the aircraft blend in with its surroundings better. And for this paint, we decided to go with the camo pattern seen to the right-hand side of the screen. And we also decided to go with a color scheme seen on the right-hand side. We chose this color scheme in this pattern because it makes the planes less visually detected from above and below when the aircraft is in the air, because it is the general color scheme of the sky, and the darker colors also allow it to be less visually detected at night. The anti-sun glint paint also helps reduce window glint, which allows the aircraft to not have as much window glint while it's flying, because there's no sun rays bouncing off the aircraft against the window, making it brighter, which reduces visual detectability. Also, acoustic detectability, the first thing we decided was the prop over the jet. Props are noticeably quieter than jet engines, which aids in reducing acoustics. The other way we reduced acoustics was by adding insulation around the engine to damper some of the noise. Next slide.
After the design process of the BC-1 Rock Python is complete, the Boeing Constructors Group was able to perform an initial cost estimation. This cost estimation was broken up into 3 separate sections, with the first being the non-recurring developmental costs. These development costs include the entire engineering development, the certification of military airworthiness, and the acquisition of various tooling and manufacturing means. This total came out to be $516.1 million. Next, an acquisition cost estimate for a fleet of 50 aircrafts was undertaken. This included the engineering for the entire fleet, as well as tooling and manufacturing, quality control, and the engines and avionics supplies for all 50 aircraft. Finally, a yearly operational cost, assuming 1,200 hours of service per year, was completed. This came up to be $369 million and includes all of the fuel costs, the crew overhead, as well as any potential maintenance costs the BC-1 Rock Python would encounter during operation. It's noted that the acquisition cost of the aircraft is high. However, as seen throughout the presentation, survivability has been one of the main topics. And we believe as a group that the increased survivability rate of the aircraft will, over the lifetime, decrease the total cost and make it more comparable with various other light attack aircrafts. The final design of the BC-1 Rock Python comes out to a total length of just under 44 feet and a height of just over 21 feet, and a wingspan of just under 46 feet. The gross weight of the aircraft is 24,721 pounds and is powered by two Pratt & Whitney 123 turboprop engines. The crew station is designed to carry two crew members, one pilot and one navigator, both equipped with K3600 ejection seats. Inside of the crew station, the pilot will be able to operate the aircraft using a state-of-the-art glass cockpit and a side stick joystick. The takeoff distance is 3,653 feet, while the landing distance is just under 4,000 feet without the use of reverse thrusters. It's noted that both of these takeoff and landing distances are under the 4,000 foot requirement set forth. The aircraft has a range of just over 1,000 nautical miles and a service ceiling of 47,683 feet. The service life is 25 years long, which brings us to 30,000 hours using the same estimate of 1,200 hours per year. The various weapons packages of the aircraft, along with the combination of its ability to operate out of nearly any field the military would need it to operate of, allow the BC-1 Rock Python to be the ultimate frontline support aircraft, being able to complete a wide variety of support missions, including large copper bombing missions or individual strike missions, while also being able to operate in nearly any scenario around the world. Thank you for coming and listening to our presentation of the BC-1 Rock Python. We will now be opening the floor to questions, beginning the Q&A portion of our presentation.
Okay, I think I'm the only audience here. So great job, everyone. And for your presentation, let's see. I think I cannot see anything like structure analysis, performance analysis, and stability analysis. Why you guys choose to skip those very important part?
Yeah, in terms of structural analysis, I believe we did a structural analysis on the wing box, and I don't believe we included that. In performance analysis, I'm not sure. I don't remember who did that. Do you guys remember?
Yeah, it was spread out across various members, tackled various different parts of the performance. We feel like the presentation was more of a pitch of the aircraft, trying to sell it towards a group of investors rather than going over all of the individual technical details. And as we practiced, we were trying to get within the 30 minutes time frame, and we felt that a lot of the technical jargon and going into the really, really weeds of every single part of the aircraft was going to bring us way over the 30-minute time limit set forth.
Yeah, yes, I agree. So we only have 30 minutes, and we need to use the 30 minutes to present the project we had done for the whole semester. So of course, we cannot cover everything. So and we need to select what are the topics that are most important. And for the aircraft design, let's say, as you said, it's a pitch, and we want to show like, let's say we are doing this as a proposal and we want the customer to buy our proposal. The most important thing is that our design satisfy all the requirements. So we want to show that from structure analysis, our structure will not fail. From the performance analysis, we want to show that our design satisfy all the performance all the like landing distance, takeoff distance, service ceiling, range, endurance, and everything. And for the stability analysis, we want to show that our aircraft has the stability in the longitudinal direction and your stability, and also the roll moment stability. So direction and lateral stability. And so I would consider those are very important part. And for the part I don't think that is that's necessary. It's like what weapons you need to use, and let's say what else. So you spend like significant amount of time on the weapon selection and the layout for heavy bomb, mixed bomb, rocket, and everything. So if we really want to skip something, we can skip that part. We can just say, okay, our aircraft has the capability of carry 3,000-pound payload, and that should be enough. Because the requirement is not like, okay, what kind of weapons you have to carry. The requirement is that the payload should be at least 3,000 pounds. That's it, right? So I understand that within 30 minutes we cannot like do a presentation cover everything in detail. That's why I said we want to include the most important thing. The most important thing here is, of course, wing design. You already have it. Tail design, fuselage, crew station, landing gear. Weapons is not that important, as long as I know that is exceeding, you have the capability to carry exceeding 3,000 pounds. And then with this design, we need to prove to the audience that our design is structurally safe, has the stability, and satisfy all the performance requirements, right? That's how we make our presentation really persuasive. Our design is really a good design, and you should choose our proposal, right? And so let's start from the slides from the very beginning. So from the first slides is the requirements. That's great. That's very important information. That is like the guidance of the whole project. And then you start from wing design directly. So if you remember in this semester, from the initial requirement to the actual design of wing and tail and fuselage and landing gear and everything and engine, we have an initial estimation based on requirements, right? So based on the requirements, let's say simply from the takeoff distance, landing distance, and like survey ceiling, everything, we don't know how to use that actually guide our design. We use that to have initial estimation. What should be the weight? What should be the thrust weight ratio? What is the wing loading? What is the lift drag ratio? We have that initial estimation, and then we use that initial estimation to guide our wing design, tail design, power plant selection, fuselage design, and everything. So it'd be nicer if you, in the presentation from the big picture, you have the initial estimation result showing at least in one slide and spend like 10 seconds there, right? So to show all the parameters, and then we can use that, okay, there's a thrust weight ratio requirement, and we have the initial weight estimation. So we know that when we do the power plant design, we know what is the target thrust we need to generate. And for the wing design, what is the lift our design wing should generate, or lift drag ratio, right? Or wing loading. So that is for, sorry, in detail. And for the wing design, so is there a page number? Next slide. Yes, this here. So the three you put as the critical flaps, I feel that it's all too big. You know what I mean? So flaps is right now what I can see from from this CAD drawings, it's like it take up almost half of the whole area of the wing. I think is too large. You can do some research on the critical flaps. Is actually very much smaller in terms of the area. So check on that and make sure that you can revise that in the final report. And the next thing is, let me check. The tail design is the conventional layout of the tail design. Yes, here. So from this picture, so you said here conventional vertical horizontal tail structure with control surface. So I would imagine that small area on the vertical tail is the rudder, right? Is that big enough?
So for one of the things, I'll point out that there was a graphics error with the image here. So we do have an elevator, you just can't see it in this image.
Okay.
And for the rudder, it is small, but that's how we calculated the size of the rudder that we needed.
And is it good enough for when you do the stability analysis? It's good enough for the to provide the stability of your aircraft, directional stability. Okay.
Yeah, so mathematically it all worked out.
Okay. Okay. If it's big enough, then for your calculation, then it's good. But just when I look at it, I feel it's like a super tiny rudder. And also
Yeah,
you said the
shaped a little oddly.
yeah, the elevator, is it so it's not on this picture?
Yeah, that's just a graphics error, but I can give you like the specifications for it if you'd like.
Oh, then it's fine. So I just want to make sure that you actually have that in the final report, because
It does exist, yes.
yeah, if you show this one in the final report, people will feel weird. Where you said this control surface, where's the control surface, right?
Yes.
So just like very small details, we need to be careful. And what else? So the stealth consideration, visual detectability, acoustic detectability, and for the graph to the very right, what is that about?
Like the blue squares.
Yeah.
That was our color palette selection. Those were the colors that we were going to base the camo pattern right next to it on, instead of the green colors, just so it blended in with the sky better.
I see. I see. Yeah, thank you for your clarification. I think it makes sense now. And for the final design, so you put everything on one page, and the landing distance 3999. Is that calculated results?
Yes, actually, it is a calculation result.
That's right. Oh, the
Yeah.
4,000, and now you calculate results 3999. It's like,
No, yeah, it is, and it is also noted that that's without the use of reverse thrusters. Turboprops are capable of using reverse thrust, and so with the additional use of reverse thrust during landing, that landing distance will be able to come down even further.
okay, that's good. So another thing that is not your mistake, or I want to criticize on anything, I'm just curious. So you put the final design, okay, your service life is 30,000 hours at 25 years. How did you qualify that based on your design?
So the 30,000 hours was just used or taken from the cost estimation. When we did the cost estimation for yearly operational costs, we did 1,200 hours per year. And the service life of 25 years was the requirement for the project. And so we just multiplied 1,200 times 25, we got 30,000.
Yeah, that's what I feel. So it's basically you just move the requirements here. It's not something analysis you did for your design. And then, okay, my aircraft has a capability to survive 30,000 hours at 25 years, right? So that's what I feel. Okay, thank you for your clarification on this part. I think that's all the comments I have. And overall, great job. And also like the whole semester, I think your group did an amazing job. And so congratulations. And
Thank you.
you're welcome.
Thank you.
Thank you.
And
Thank you.
keep working hard on the final report.
So for the final report, Dr. Ting, do you want us to follow kind of the same pattern you were describing for the presentation here, where we kind of start with the initial estimation and then roll into the development?
Yes, so we want to have a big picture for the final presentation. So let's say you start from the requirement from the proposal, the request for proposal, and then you have initial estimation. So you have everything, like you have the parameter, but that part, it does not need to be as detailed as what we did in the mini report, because in the end it has 100-page requirement, right? So if you put like the whole thing, calculation, iteration, and everything in the report, it probably take like 20 pages. So I would say that put the methodology there and put the final results there. You do not like to put a lot of content there, but we want to see that part. So the initial estimation, we want to say what is the initial estimated weight, takeoff design weight for the ferry mission, for the design mission, what is the thrust weight ratio at takeoff situation, wind loading at a takeoff situation, and also the lift drag ratio, and how did you estimate that? But it does not need to be like very detailed. Okay, this is first iteration, second iteration, third iteration. No, it does not need that detail. And then based on that, okay, I can say based on the lift drag ratio, the lift coefficient required at takeoff and landing, and the lift coefficient need required at cruise, and wind loading and everything. We use that to guide our design. So what is the wind design? Right? Why do you want to choose airfoil? Why do you want to have the table ratio, dihedral, everything? So, and then for the wing design at the end, for a completely designed wing, we have a performance analysis. As I said, you put this design wing in a software, any software you are familiar with, and you prove that, okay, this design wing does actually have the lift coefficient something at cruise, and at takeoff landing, when I extended all the flaps and everything, it has capability to have some certain lift coefficient at takeoff and landing, right? So we can say, okay, the wind design part is done, and for the power plant design, from the initial estimation, we have the thrust weight ratio, we have the initial takeoff weight, so we know that what is the thrust required, or what is the for your aircraft probably is the power to weight ratio. So what is the power required, right? And use that one as guidance. So, okay, this is our snack engine, and this is the propeller, and this is like everything in detail. And in the end, okay, we can say that our engine can generate certain what is power and what is thrust, and it does satisfy the requirements. And also for the structure, okay, what material we use, what kind of the structure we use, like the semi-monocoque. And for the wing design, we actually did analysis for the wing structure, and the most critical place is at the wing root and at the top and bottom. And based on our design synaptic material, the maximum stress of the wing structure is lower than the allowed stress, or there's a safety factor. I would want to see something like higher than 1.5, and we can say, okay, structure part is done. And then we have like tail design and everything. And then after we have the tail, fuselage, cruise station, landing gear, wing, and everything, I want to see a, of course, weight estimation and a center of gravity estimation, and because that is basically for the stability and control analysis, right? So we want to make sure that our design aircraft, the whole thing has the longitudinal stability, lateral stability, and directional stability, right? So that is for that part, you need to make the derivative of each part within the reasonable range, and also we want to see in the end a performance analysis. So the calculated takeoff distance, how did you calculate it, landing distance, and let's say service seating, you need to put the operating envelope there to show that, and also that envelope includes service seating and everything. So that is like from the big picture and from the each chapter, a small picture, you want to make it like everything is logically collected. And then you can say, okay, this is the whole report, it's our design.
Cool. Thank you very much.
You're welcome. So any other question?
Was
I
there
had
a page? Oh,
I had a clarification question on the 100 page limit. Does that include like all of the CAD drawings and like the reference pages and everything, or is that just like, you know, the content of it? Because I think we've got like a ton of CAD drawings, so I just want to
I
back
think
that
it's
up.
everything.
Okay.
Yeah, so for the CAD drawing, we have a tons of CAD drawing in the process. So let's say when we design wing, we have the wing. When we design landing gear, we have landing gear. And when we design tail, we have tail. But for the CAD drawing that you need to include in the final report, you need to read the request for proposal. They have a list what the CAD drawing that you really need to put into. So probably most of the time you want to put the whole thing there, right? And you can check that one in detail and see what are the actual CAD drawing you need to put in the final report.
Okay, thank you.
You're welcome. Any other question?
There is something that I'm scratching my head over a little bit. So you did mention in the beginning that we're supposed to like include performance analysis parts and like stuff on stability. I get the part about putting stuff on performance analysis, but like when we did a stability part, we had like a bunch of big equations with like derivatives in it, and you said in the lecture about presenting that we had to appeal to people of different backgrounds, even those that didn't have a technical background. So I wouldn't see how like including like the stability part
Well, actually,
calculations would help in this presentation.
You mean in presentation, right? Actually, in I have started from 9 a.m. From now, this is the last one. So I would say that all the other 6 groups, they include the performance analysis there. So it does not need to put the equation there. So I think that most of the group, what they did is that, okay, so this is takeoff distance, it has ground roll, it has the transition state, it has climb, and our calculated result of the ground roll is some value, the climb is some value, and the climb transition, climb and everything, and then these 3 values we add together. Okay, so this is the takeoff distance, and same thing for landing distance. There's an approach, there's a flare, there's a ground roll, and what is distance we calculated for the approach, what is distance calculated for flare and ground roll, and we add them together. Okay, so this is our landing distance. You do not need to show the equation to the audience as like general audience who is not in the aerospace. No, but you need to show in the level that I just said. and I think they can accept that level of information.
Got it. Thank you.
You're welcome. Any other question? Okay. So thank you for the presentation today. You all did a very great job, and keep working hard on the final report. And that's it. Have a great day.
Thank you. You too.
Thanks. Have a good
Thank
day.
you.
Thank you.
thank you.
Bye.
Bye.